Hey everybody. I just wanted to do a couple problems that were on the review. And so I did pick these ones for a reason, but that doesn't mean you should just study the three that I'm about to do. Study them all, but pay special attention to these ones. So number 17 says the graph of the function f of x equals x cubed minus 4x plus 5 has, and then a whole bunch of stuff here. So I'm going to highlight what's important. So it says two relative extrema and one inflection point. One relative extrema and one inflection point. So there's kind of a pattern, relative extremum or extrema and two inflection points. And it might not be two inflection points, but basically it's kind of a weird way of saying how many relative extrema does this have and how many inflection points does it have. So in order to figure that out, I am going to need to take a derivative and a second derivative. So to do the first derivative, it's just going to be the power rule, 3x squared minus 4. Derivative of 5 is 0, so we're good there. And then I'm going to put the second derivative over here because it's asking about relative extrema. So I know I need to find the critical points, and it's also asking about inflection points. So I need to find where the second derivative is equal to 0. So I was going to give myself space. So second derivative would be 6x. And derivative of 4 is 0, so that just goes away, which is very nice. So let's start with the critical points. So I'm setting it equal to 0, but one thing to remember is that critical points are not just where the derivative is equal to 0, but it's also where the derivative is not defined. But 3x squared minus 4, that's defined everywhere, so I just need to set it equal to 0 and solve. So I'll add 4 to the other side. 3x squared equals positive 4. Divide by 3, x squared equals 4/3, or x equals plus or minus 4/3. So this is kind of like a thing to note. Notice I said plus or minus. Maybe put that on the note card. Put on the note card. It's really easy to forget, and your calculator doesn't always tell you that something is a plus or a minus. But in this class, if you have a square root, like if you take the square root of something, it could be the positive and it could be the negative. So we have two critical points, and let's also write these are my critical points. All right, now for inflection points, I would set this equal to 0 or look to see where it's undefined, but 6x is defined everywhere. So dividing by 6, I get x equals 0. So this is a possible inflection point. So notice that it says inflection points. So I need to know for sure. And actually this is kind of helpful. I know it can't be this one. And there are two critical points, so this helps also. It can't be, well actually this one says relative extrema, so I can't knock anything out yet. But what I can do is make some number lines. So for my possible inflection point, I'll put 0 in. And then for my critical points, I'm going to put negative square root 4/3 and positive square root 4/3. So 0 would be in the middle. And now I need to test points. So actually over here on the left, this is actually pretty easy to test points. Let's choose -1. If I plug in -1 into my second derivative, that's just going to be -6. So it's negative before 0. And then if I plug in 1, I will just get 6, so I get something positive. So actually this is very helpful. There is one inflection point because the concavity changed from negative to positive at this possible inflection point. So we know that it is for sure an inflection point. So my two possible options are A and B. Because I know it's not no inflection points, and I know it's not two inflection points. I guess it could also be E, which says none of the above, but I kind of doubt it. So over here, so actually there's something kind of cool here. We can use the work that we did on the left side here to help us with what's happening on the right side. So one thing we learned in this class is that if you test a point in between critical points like that, so 0 would work, then it has to be the same on that whole interval. So I'm going to combine what I have on my left and on my right. So at negative square root 4/3, I know that that's on this side over here, somewhere in there, negative square root 4/3. I should be careful. I know that this is concave down. So concave down looks like that, which means this would correlate with a maximum. And then on the right side, I know that it's positive, concave up. The second derivative is positive. So this one has to correspond to a minimum because it's concave down there. So that's actually great. That tells me that there are 2 extrema. So I can come up here, and that looks like problem A. So I'm going to write that out because well, actually, I'll just erase. So process of elimination and a little bit of work. That is A. Okay, so if there are questions on this, please do ask. But since this isn't live, I'll just go on to the next problem. So I don't want to give too much away, but 100% you should be prepared for this problem on the test. You know, I'll just leave that out there. So number 28, a company knows that they will sell 10,000 cases of good stuff at a steady rate over the course of the next year. So this phrasing here, steady rate over the course of the next year, that's kind of like a hint that this is this style of problem. So it lets us know that it costs them $10 a year to warehouse each case. Okay? Based on the average number of cases in the warehouse. Okay, and it costs them $150 each time a delivery is made to their warehouse. How many orders? Okay, so one thing is going to be the number of orders, one of our variables. How many orders should they place each year in order to minimize their total inventory costs? Assume that the orders are all of equal size. Okay, so one of the things is the number of orders, and then the other number is number of items in each order. So it's the size of the order. And I guess instead of item, I could have put good stuff. So let's call, let's see, how could we, tricks for remembering? Well, let's just call this X, and Y is the number of items. Okay, so there is a kind of a trick to this problem, which is why I recommend putting something like it on your note card. But the trick comes in this part right here. So it costs them $10 a year to warehouse each case based on the average number of cases in the warehouse. So the number of items in each order, so that's how much gets delivered. So let's say on the first day of January, Y items are delivered. And that makes sense because that's the number of items in each order. So basically you got a delivery. And then we're told that they sell at a steady rate. So at a steady rate, those items leave the warehouse as they're sold until 0. And then if whoever owns this business is smart, on the day that they run out, they would get a new order. And so that order has to be the same size because that's an assumption of this problem, is that the order is going to be the same size every single time. So it's the same size, so it's again Y, and it's going to leave the warehouse at a steady rate. And then as soon as they get to 0 items, right, that's what 0 would be here. As soon as they get to 0 items, whoever this is would order again Y units, and Y units would get delivered, and it would leave the warehouse at a steady rate. So then the question, what's the average number of cases that are in the warehouse? So it's kind of weird, but it would be the average, which would be halfway, Y over 2. So the average number of cases in the warehouse is Y over 2. So we're going to add this as like a little trick here. Average number of cases in warehouse is y/2. So instead of drawing a picture, I just want to go over that one more time, but just in words. So every time they get a delivery, that's when they're going to have the most that they're ever going to have. So they get a delivery, it goes away, you know, over time, people buy it until there's nothing in the warehouse, and that's the least they're ever going to have. So this keeps happening throughout the whole year. So the average amount of cases that they'll have in a warehouse is halfway between those two, is y/2. Okay, so let's read the problem one more time and see if we can pick up more about what we're supposed to be doing. A company knows they will sell 10,000 cases of good stuff at a steady rate over the course of the next year. So actually that is helpful. So what we know is that the constraint is 10,000 boxes, right? Let me slide back up. 10,000 cases. Not more, not less. And it costs them $10 a year to warehouse each case based on the average number of cases in the warehouse. Okay, so that's telling me that it's $10 times the average number of cases, which we just found was y/2. And this is just like the carrying costs, like the cost to house it. Okay. And it costs them $150 each time a delivery is made. Okay, so there is a $150 fee every time there's an order, and we know there's going to be X orders. So that's going to be like the delivery cost. How many orders should they place each year in order to minimize their total inventory costs? Okay, so I'm going to say that the inventory cost is going to be the carrying cost plus the delivery cost. So 10 times y/2 plus 150 times x. And this is my objective. I want to make this small. Okay. So I am seeing one trouble, and that is that my inventory cost is a function of two variables. So now I need to think about how my constraint equation relates x and y. So the way I usually do this is I kind of break it up like that. So 1,000 cases, or 10,000 cases, I need to figure out how that relates to x and y. So it helps me to remember what x and y are. So x is the number of orders, and y is the number of items in each order. Okay, so y doesn't change, right? Y is the number of items in each order, and that's going to be the same each time. And x is the number of orders, and we're trying to figure out what that number is. But if I knew x and y, the number of orders and how much was in each order, I think x times y would be 10,000. Which is a perfect constraint equation. So I'll use my constraint equation to eliminate one of these variables in my inventory cost equation. So I'll divide by x, and that gives me 10,000 over x equals y. I can use this constraint equation to rewrite my inventory cost equation. So let's see, 10, and actually that's just 5y, 5 times 10,000 x plus 150x. Okay, so this is the thing I need to minimize, which I'm going to give myself this space here to work. So I need to minimize that. I'm going to start by kind of cleaning it up. Initial costs equals 50,000 over x plus 150x. I would rewrite this so that it's 50,000 x to the negative 1 plus 150x. That way, when I try to find the critical point, it's easy to just use the power rule. So now I'm going to take the derivative, negative 50,000 x to the negative 2 plus 150. So I've got the derivative. I'm trying to find the minimum. I'll set it equal to 0. And actually, just one thing I should mention. I've said this before in this very video, that just because you take a derivative and set it equal to 0, that doesn't always mean you're done. You do also need to think about where the derivative is not defined. And one place that happens is when x equals 0. The only trouble with that, the reason why I'm ignoring it, is x equals 0 is the number of orders. So I just don't think that can be right. It can't be right that the minimum is when you don't order anything at all. Like, it's kind of useless. You have to order something in order to have something to sell. So I'm going to ignore that, set it equal to 0, and try to solve. So I'm going to add 50,000x to the negative 2 to the other side. So I get 150. And I'm even going to rewrite this as 50,000 over x squared. Then I'll multiply x squared to the other side. And then I will divide by 150. And then I will square root. And I'm going to keep the positive square root because it wouldn't make sense to have a negative number in this case. Okay, so I'm using a calculator, which you cannot see. 50,000 divided by 150. And then I want to square root that. Let's see, does that work? Oh, good. Okay, that is roughly 18.26. But I'm going to round to 18 because it doesn't make sense to have part of an order. So let's go see if that's one of our options. It is one of our options, so I bet that's right. So I want to go back and mention that because I said it in passing, but it's actually pretty important. So when I put it into my calculator, I got 18.26, but in this case, it doesn't make sense to have a decimal because x represents the number of orders, so you can't have like half of an order. That would kind of defeat the purpose of the whole problem. So I just rounded to the nearest whole number, which was 18. So this is kind of an interesting problem. Definitely be prepared for it on the test. If you have questions, do ask on the discussion board, but I'm just going to scoot on to 35. So for all x in the interval from 0 to 15, the function has a negative first derivative, so that means it's decreasing, and a negative second derivative, so that tells me it's concave down. So putting those two items together, it looks kind of like that. Or in words, you could say that it's becoming more and more negative. And actually, that's not a good way to say it. It's not that it's becoming more and more negative. It's decreasing more and more. And the values might be positive, but it's decreasing more and more. So the way I would do this is I would look at all of these and figure out which ones are decreasing. So this one appears to be increasing, so I ignore that one. And this one does too. This one's decreasing. This one is also decreasing. And so is this one. Okay, so now I'm looking for something that decreases more and more each time. So starting with part C, and I don't want to circle it in case it seems like I'm saying that's the right answer. So it goes from 1.2 to 1.9, so that's like subtracting 0.01, and then from 1.19 to 1.14, that's like it's subtracting 0.05. And then this one looks like it's subtracting 0.1, negative 0.1. So to me, this one does, I'm going to guess this one at the moment because it decreased 0.01, and then it decreased even more than that, and then even more than that. So this is a very good possibility. This one looks like it's decreasing less and less each time. So it went down by 0.1, then by 0.05, and then by 0.01. So I think this one is decreasing less and less. And then this one, 1.2, okay, so this one, it's the same each time. You go down by 0.01 each time. So this one is just decreasing linearly. So I do think the answer is C. All right, so if you have any questions about any of these problems, do let me know.